Let's take a look at an example involving ANOVA and a table. So the General Social Survey collects data on demographics, education, and work, among many other characteristics of U.S. residents. Using ANOVA, we can consider educational attainment levels for all 1,172 respondents at once. So just some scratch work on the side here. My capital N, the total number of individuals that were sampled was 1,172. Below are the distributions of hours worked by educational attainment and relevant summary statistics that will be helpful in carrying out the analysis. So I have less than high school, and then I've got the average number there. I've got high school, junior college, bachelor's, graduate, and then an overall total here. So I've got the mean, the standard deviation, and the number of samples in each of these categories. So again, these are the hours worked by educational attainment. So I have 38.67, 39.6, 41.39, 42.55, and 40.85. So a natural question might be, write the hypotheses for evaluating whether the average number of hours worked varies across the 5 groups. So I might be curious if there's a difference in how much these 5 different groups work. The null hypothesis for comparing all these things is going to be that they look the same. So the average worked for less than high school group 1 is the same for high school group 2, junior college group 3, bachelor's degree group 4, and graduate studies group 5. If any of these results are different, we would reject that null hypothesis. So the alternative is going to be at least one is different. They give us a partial table and they ask us to fill it in, to calculate the test statistic, the p-value, and the conclusion. So let's take a look at that together. I copied down the information that they gave me in the table. And I had 1, 2, 3, 4, 5 different groups that I was looking at here. When I'm comparing multiple averages at the same time, I'm looking at an analysis of variation, ANOVA. And this uses the F distribution. The F distribution has 2 degrees of freedom. It has a degree of freedom for between the groups, and that's the number of groups minus 1. And there's a degree of freedom within the groups, and that's the total number of values minus the number of groups. The between is often referred to as the treatment. In this case, the different treatment would be the level of degree. The within refers to how much each of those groups vary. So it's telling me how much error I have within each of those groups, the degree of freedom of the error. I had 5 different degrees that I was looking at. So the degree of freedom there is going to be 5 minus 1, or 4. My other degree of freedom for the error is going to be 1,172, the total number of students, minus the number of groups, 5. And when I do this, I get 1,167. When you're looking at these tables, sometimes they use different language. If this uses the language of residual, residual is another word for error. My treatment here, or the thing that changes for each of the group, is the degree level. So my treatment would be here. So my degree of freedom for the treatment, my degree of freedom with between my groups is 4. For my residuals, my degree of freedom was 1,167. My total degree of freedom, if I add these together, is 1,171. Your total degree of freedom will be equal to the number of values minus 1. Now it gives me some mean square and sum of square information. To get those, I need just a tiny bit more to work with. And what's going to be helpful here is that the mean square for the treatment is the sum of the square of the treatment divided by the degree of freedom. Likewise, the mean square of the error, the MSE, is the sum of the squares of the error divided by the degree of freedom for that group as well. There are longer formulas for finding the sum of the squares of the treatment, and you might have to use those for other problems. So for example, you might have the number in each group, individual averages minus the overall average squared, divided by the number of groups minus 1. That's the larger formula for that. Now, luckily, they're giving me a lot of that information already, so I don't have to use this longer calculation. Likewise, there is a longer formula for finding the MSE. That's the sum of the individual degrees of freedom times their standard deviations squared divided by the total number of terms minus the number of groups. But again, it's giving me a lot of information by giving me some of these sum of the squares and degrees of freedom to work with. Let's start with the mean square for the error. So if I'm labeling these things, sum of square of treatment, this is the SST. Mean square for the treatment, this number is the MST. Sum of the squares of the errors, this is the SSE. Mean square of the errors, that's the MSE. And we'll begin by calculating the MSE. I'm going to take the sum, 267,382, divided by its degree of freedom, 1,167. So I'm taking the sum divided by the degree of freedom, and that will give me the mean square. I'm dividing things out to essentially get some sort of an average for the sum. So if I type this in, 267,382 divided by 1,167, I get 229.12. If I'm trying to find this sum of the squares of the treatment, it's giving me the MST, so it's going in this opposite direction. So if I plug in everything I know so far, it gave me the MST, 501.54. It didn't give me the SST. And the degree of freedom is 4. So if I try to set everything up here, my MST, my SST, and my degree of freedom there, I can solve for that missing number. So to go from the sum to the mean, it looks like I need to divide. To go in the opposite direction, I would need to multiply this over. When they give you partial tables like this, it's kind of like a puzzle. And that gives me 2,006.16. 16. The table wanted to know the sum of the squares for the total, and I can find that by just adding those two numbers, 2006.16, 267,382. That gives me a total of 269,388.16. We don't use those totals on the bottom when we're doing our ANOVA calculation, but they're good to know. The last square that I'm missing is my F score. In my F ratio, this is like my z-score, my t-score, my chi-squared. This is my test statistic. And I find my F score by taking the mean square of the treatment divided by the mean square of the errors. The t is on top, the error is on bottom. So I'm going to take that 501.54 divided by 229.12. When I do so, and any number bigger than 1 is considered a large F score, I get an F score of 2.19. So that's large, but I don't know if it's statistically significant or not. To look that thing up, I could use technology like GeoGebra. So going into GeoGebra and into probability, I am working with the F distribution. It asks for the first degree of freedom. That first degree of freedom is going to be for the treatment, and that's 4. It asks for my second degree of freedom. That's 1,167. It's always going to be a right-tailed test. And the number that I'm typing in here is 2.19. And doing so, typing my F score there, gives me a p-value of 0.0682 or so. So they already gave me the p-value, but I could use GeoGebra to double check my work. That number's looking pretty reasonable. Going back to this hypothesis test, my F score was 2.19. That's my test statistic. My p-value, they gave me in the table, the GeoGebra gives me the same thing, 0.0682. Final step, conclusion. My p-value is bigger than or equal to a neutral alpha level of 5%. I would fail to reject the null hypothesis. So I do not have evidence that the average number of hours worked varies by the level of degree. So that's good news. There's no evidence of a difference between those groups. I'm going to type these results inside of MyOpenMath and check things out. So null hypothesis is that they're all equal. At least one pair of the means is the same. No, so there's no requirement that any of them need to be the same. At least one of the means is different. That's what I'm looking for. The next one would say all of the means are different. That would be a problem. This last one's a little bit funky because for some reason it tosses in a 6th group. Weird. But I am looking at this. I have 5 groups. I'm testing that at least one is different. Degrees of freedom, 4, 1167, 1171. Some of the squares, these are really large numbers. 2006.16, 269,388.16. It's It's entirely possible that I could have typed something in wrong when these numbers are this big. So it's a great idea to double check. 219.12. My p-value it gave to me. My f value, or my f score, is 2.19. And that's the same thing as my test statistic. The p-value was 0.0682, and it gave that to me inside of the table. My p-value is bigger than or equal to alpha, so I'm looking at one of these three options up here. We have evidence to support the null hypothesis. No. We reject the null hypothesis and have evidence to support the alternative. I don't think so. We do not have evidence to reject the null hypothesis. Great. Checking that out, I did get full credit. Cool. So I must have typed all of those numbers in correctly. Again, to find these values inside of the table, there are really three key formulas. The MST is the SST divided by the degree of freedom. The MSE is the sum of the squares of the errors divided by the degree of freedom. And your F score is your MST over your MSE. These are computationally more heavy problems. They do something pretty amazing. This has compared 5 averages with one calculation. Pairwise, you'd have to compare 1 to 2, 1 to 3, 1 to 4, 1 to 5, and you do a ton of individual tests. The fact that ANOVA can do all these tests in one fell swoop is pretty cool.